bit.ly, and then it's CSC-200 winter. Now, that'll stay out there. You can keep doing that. But if you want something a little easier, if you're still keying this in, if you haven't bookmarked it, just put C4E.us. Now, what the heck does that stand for? Well, C4E means computers for everyone, and the .us is like .com, except it says us. So 5 little characters and a dot will get you to this page here. And the reason for this page is, as I've been telling people about these techniques for doing things online, I just figured it was nicer if I put up one page. Oh, well, you can't see it too well. I wonder if we have a volunteer to go over there and turn the lights on. Okay, so this page is easier to get to. It's just an index to the 3 different courses I've been doing online here, and a couple of pictures I thought were kind of cute. Some of them I found on the web. And this little guy here, I just took that picture the other day because I got an iTouch. The new model of it has cameras in it. And I was just playing with it the first day I had it. And I went visited a friend who has this little dog. And so I took a picture of the dog. Well, I'll put that up there too, why not? So these are the 3 courses I've been doing. And of course, if you click on this one, then you'll come to this page anyway. So it's just an easier way of me telling people how to get to these things, and I only have to tell them one address. If you go here now for the second unit, what we're going to be talking about is really the evolution of commercial computing, but not at a bits and bytes level. More the trend that I want you to understand so that you get this big picture of it. And the only thing out here right now is this bunch of readings. So if you click on this, you'll go here and be able to select Chapter 2. Chapter 1 is what you got last week. And if you wanted to, you can copy that and print it. I'm actually inclined to just continue to package this up as electronically available readings. And in the past when I've done this, they've usually gone into print afterwards. But in this one, I think I'm just going to leave it electronic. And over the course of the term, I'm going to be kind of curious to get some input from students on what form you might see that being most convenient. I would just put it out in PDF ordinarily, which would be readable on the screen. But if you're using a small device like an iPad or even a phone of some type to do readings, I'm curious what format might fit better in that environment. Because I really think the future of this should be electronically available materials like this that are written for the class, and not these expensive textbooks that just go off. It's ridiculous what's happening with textbooks. They're just way too expensive, and they're stale. I can provide much more up-to-date information this way, and you don't have to pay for it. Plus, I can include links, and that's what you're going to see in this one. A lot more use of hyperlinks. So if you right-mouse click on this and do a save, that's all I did. That's how I got this workbook already. So I'm not going to save it again, but I've already got it here, and I'll just open it up. Now, the best way that I've found, in case you're not familiar with this, when you're reading this stuff, just to get a big picture of it, is to go to View and then go to Full Screen. So if you do this, you may still be able to read it on the screen, but you could use the arrow keys to go through it page by page. And that's what I'm going to do to start, just to give you a big picture of what this material we're going to talk about looks like. So there's about 7 pages of it. It actually is well indexed here. And let me go back for a moment to this view of it. What we're going to be talking about is from the start of commercial computing in the 1950s and a little bit before, where these computers came from and their orientation, how people thought about using them. And then we'll talk about, through the years here, we'll just see how the architecture, that is, the whole arrangement of the computer changed over this period of time till now we're looking at something called cloud computing, which I'll touch on as we finish up today. But this is just a big picture of computing, because the course really is a survey of computing. And at this point, now that you understand something in the first unit about how machines store information, I want to just take a look at how the machines have evolved over the last 60 years and very quickly bring us up to the present. So let me do that right here. And what we're going to do, we'll be looking at the oldest of the machines, these experimental machines from the 1940s, and how they filled up a whole room. They led into what we call mainframes that also filled up a whole room in the 1960s. And more importantly, the orientation of those machines. How did they expect to be used? How were they designed to be used? Which is far different than the way people think about computers today. And then some diagrams like this that start showing you how those early machines were adapted to more modern processing, like online processing, where you're interacting with the computer. And then how it changed after that when people started manufacturing smaller computers, not desktops, but mini computers, and how that changed the scene. And then when PCs came on the scene, how that changed the way that computers were configured for a business. And then the changes since 2000 that have occurred, where the oldest hardware is now wheeled out in many locations, and a whole different approach is being used, but still with a centralized organization running the hardware. And then finally, towards the future, where some people are predicting this sort of a thing, that we won't even have to have hardware operated by an organization, but instead, because vendors like Google and Amazon and Microsoft, they've had to develop huge amounts of computing power for their own businesses. And the idea that came about was, well, you can tap into their computing power as much as you need, as little as you need, because the high-speed internet connects you to it. And so you just buy it as a service, just like very few people these days have their own electric generators. Instead, you just have wires coming in from someplace else. Somebody makes the electricity, and you buy it. As much as you use, you pay for it. Well, the same thing for computing services, except it's a little more complicated. So there are things that people are still considering about it. But already some businesses are doing that and saving themselves the cost of the equipment and upgrading it, the software, keeping the thing secure, a premises to run it, all the high-priced people to do the care and feeding of it. But all of that sort of outside. So the business focuses on what unique use they make of software to improve their business rather than all this infrastructure sort of stuff. So anyway, that's what the lecture looks like today. And one of the exercises, one of the projects is up there now. This one is kind of typical of what you'll see in terms of these exercises with a lot of built-in hyperlinks. So if you're interested in this one is a technology timeline where I'm asking you to pick out the dozen most important events and inventions in the last century that led up to this point. And I'm giving you a bunch of hints with these websites that as you read through these little 1-minute lessons, if you want to learn more about this thing, here's one of the places that you could go to. This talks about the vacuum tube, and it's just an electronic component that's pretty much obsolete now, but this talks about how it led into the development of computers. I give you a little summary of that. Let's see here. And the rest of these are active in the same way. So sometimes these links will lead to little movies, little clips of that. Other times, those things would be like an assigned video that you might see on that Unit 2 page. So that's the way we're going to be talking about things today. And I will describe for you what I have in mind for each one of those pages, illustrating it this way. I have a choice in putting up this lecture. I might just peel off what I talk about now and put that up for the lecture that you could watch, in which case it'd be very boring because you've already heard it live. But other people who hadn't, that might be the way they get it. Or if it seems to be a better approach to it, I might just record it using a little camera and then edit it and put that up instead, and that might be in little 10-minute segments. So you might, either way, you'll be able to review what we're talking about today, but it would be a very good idea if you actually read through this stuff. And it's only really just a couple of pages, because what I'm trying to do here is to focus on essential readings, which are these. And then for whatever projects you choose, go deeper. But one thing that you'll find is that these projects are always assigned for reading, because the little background I put there is interesting for everybody. And some of the exercise material comes from that. So instead of repeating it here and then here, I'm just writing it once, but then you still choose which of the two you want to do. It's just that you'll be reading about all the background on all of them. So let's take a look at this right here. And in fact, it might be better if I do this way so that we can take a look at it. So, okay, here's what happened. Even before the 1900s, some people had some ideas that it might be possible to do at least some arithmetic using a machine. And a fellow named Babbage came up with the idea of doing this, and the only technology available to him in the 1830s was gears, rotating gears. Well, you know, you could sort of do arithmetic with a gear. Think about it. If you had a gear here that had 100 teeth, and a gear here that had 10 teeth, and they're meshed, okay, I have to turn this one 10 times to get this one to go around once. So what happens if I turn this around 5 times? Well, this one goes around halfway. And if I put numbers around the dial, I could read the numbers back. So just by making mechanical motion, I might be able to, by the size of the gears. Well, a lot more complicated than that. He figured out some way of doing some kind of arithmetic. But really, it was too complex for the technology of the day. I mean, they knew how to make watches back then, and they had the technology to make gears. But it really wasn't all that developed. And so it was very tough to think about having huge amounts of gears interacting and something turning here and something coming out there. So it never really went very far. There was another way that people started using some technology to store information, and that was with weaving looms, where you have lots and lots of threads coming in, hundreds of threads coming in that are going to be sort of moved this way and that, and a shuttle go through to weave cloth. And you might see some pictures. In fact, there's a novel, Silas Marner, that sometimes people have to read in grammar school. It's all about a weaver. And these things were mechanical devices where somebody would sit there and they would push these pedals. And they push this pedal down and the threads go this way, and then you'd throw this bobbin through that carried a thread. And then you'd push the other pedal down and the threads would alternate, and you'd throw the bobbin through again. And you sit there all day doing this, one thing after another. Now we pay to do this, going to exercise. Back then they would do this just because that was going to make cloth. So if you wanted to make a pattern, you'd have to change the thread occasionally. And that business of changing the thread, if you didn't change it quite right, you wouldn't get the pattern you wanted. So somebody cooked up the idea of using flat wooden plates and punching holes in them and arranging some mechanism so that would control the changing of the thread. So you could program the loom. And I can't explain exactly how it is. There's some pictures of it out there. But the idea is it was like punch cards, only really big, with big holes in them. And by these feeding through the machine at the time that the weaving was going on, it would dictate what color thread was being used, so you could make a pattern out of it. You could automate the production of cloth with a certain pattern. See, that's information storage in a mechanical way. So eventually people started getting the idea. By the time the 1900s rolled around, some people started getting the idea, wow, we might be able to combine these things, storing information, doing things mechanically, but then electronics came along. And in the early 1900s, with the invention of radio, in fact, the time period from 1850 to 1950, if you think about somebody who was maybe lived to the age of 100, and they were born in 1850, what a fantastically large amount of change they saw from the time they were a kid till the time they died. I mean, it went all the way from people riding around on horses to the invention of the car, the phonograph to record sound, the pictures, moving pictures, then action at a distance with radio, and then television, and then the atomic bomb and computer. I mean, just from ancient times, more or less, to the modern times in the span of one lifetime. Well, in the middle of that, radio waves were discovered, and then ways to produce them electronically were invented. What happened was, Thomas Edison invented the light bulb. So what's the light bulb? Well, now we're replacing them, with more efficient ways of generating light. But in Edison's day, there was no way to put energy into something and make light. You had to burn something. That's a little bit hazardous, as witness the Chicago fire. You kick the lantern over and the city burns down. And it's dirty and it doesn't produce much light. It's dangerous. Gas replaced kerosene for a time, and people had gas lamps where you lit the gas lamp and that made light. But electricity, people discovered it and then figured out a way to make it and distribute it on wires. But how do you turn it into something useful, like lighting up the night? And Edison fiddled around. It wasn't very theoretical. He did a lot empirically, which is just to try one thing after another. And he figured out what kind of a little wire filament inside of a bulb that all the air had been sucked out of. If you pump electricity into it, it gets hotter and hotter and finally glows. Puts off a lot of heat, but it puts off light. Well, here's the light bulb. So that about 1880, that was a big deal. And as they used these things over the years, they saw that the inside of the glass got darkened. And it looked like some material was building up on the inside of the glass. And what the heck is this? And it turned out they eventually figured out, about the same time people figured out that what things are made up of little particles, atoms, but atoms have little parts to them too, electrons and other things. And they figured that this heated wire was boiling off electrons. And they were sort of flying out from it. and they would accumulate some molecular structure on the inside, and they were darkening it. Well, other people figured out they were charged negatively, and then somebody decided, well, let me put a metal plate in here to see if I can collect these electrons, and they could. And electrons are negative. They put a positive charge, which is the absence of electrons, on the plate, and the electrons all streamed over to it. But the current would flow that way, but not backwards. So if you had a current that varied, like alternating current or a radio wave, you could turn it into a direct current by using this device. Then somebody else figured out, well, wait a minute, what happens if I stick, I don't know why he did this, but he experimented by putting a little wire in between the filament and the plate. They called it a grid. And this was really momentous, because he found that just by putting a little signal onto that grid, you could control a large flow of electrons from the filament to the plate. So little signal could get amplified into a big one. This was really tremendous, because when this came along, it was the era when telephone communication was limited to about 15 miles, because the signal gets weaker and weaker as it goes through the wire. So how do you go any farther than that? You can't. You better use a telegraph and just, we'll click, 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 and that would go some greater distance. So when you put an amplifier on there, though, you could make the signal stronger again, and then it would go another 15 miles. So by 1915, they figured out how to use this device to make long-distance telephone calls. Very expensive, but you could call. It was amazing, because you could make a telephone call and talk to somebody hundreds of miles away. Well, about the same time radio was developing, and it turns out that this little amplifier could be used to generate radio waves too, and it could also function as a switch, an on-off switch. And that's what started people thinking about electronic computers. Even though that device was kind of inefficient, it took a lot of power, and you needed one whole tube, a little thing that looked like a light bulb that had these metal elements in it. You needed one of them just to store one bit. At least it was possible. And that's what you're looking at here with these pictures. This was one of many projects that were done from around the 1930s onward, where people, engineers and scientists at the universities, experimented with different ideas of how to use this electronic technology to store information in bits and arrange circuits to manipulate them, test what the bits were and make determinations like those logic gates we talked about. And to us it seems laughable that here is a huge room full of all these thousands of tubes just to do something that's weaker than a desk calculator today. But the technology at least demonstrated that these things could work. And one of the reasons, the impetus for doing this, it took a lot of money to do that, but the government funded it because the war was on, the Second World War, and they needed ways to do computations very quickly. The development of the atom bomb took a lot of computation, and they had people working with calculators, doing these things by hand. And it wasn't fast enough if the invention was going to do any good for ending the war. So it turns out the computers took longer to develop than the war. The war was over by the time these things worked out. But in the 20 years from 1945 to into the 60s, that technology was refined and actually commercialized. By the 1950s, there were some computers around, very expensive. By today's standards, very limited, but at least they did things much faster than people could do. It turns out that the word computer comes about because, we're manipulating numbers. So when computers were commercialized, the first place they were used was accounting departments. Where did you have to crunch numbers in business? So that's where computers wound up. Because they were expensive, a business would have just one of them. And the picture you see here from 1968 is a large IBM computer. By this time, the tubes had been replaced with transistors, which didn't require as much power, and they still generated heat, but not nearly as much, and they were more reliable. So the transistors kept getting smaller, and now they're packaged as integrated circuits, but it's semiconductors, materials like silicon and germanium that conduct electricity in one direction and not the other, and they can do the same thing the tube does. In the process of conducting from here to here, a little signal put here can vary the signal a lot, or you can turn it on and off. So basically, it's an electronic switch. Well, that's what we had back then. Now, the important thing for us is, how did people use these things? How did you interact with them? Well, what happened here was the way that initially these machines were developed was to say, take all your data and pile it up. And when you're ready, shove it through, and we'll update something. really what happened in most business instances was you had a master file. Let's say it was a file of the products that you had manufactured or that you sold. So how many of them in the warehouse? Well, it's going to diminish as you sell things. It's going to increase as you get more of them, buying them by wholesale. And you have to know how much you got. And then you have to send the bills to the right people who bought them and all the other accounting things. So these were stored on a master file, and the information storage at the time was oriented to magnetic tape, just like a VHS tape, about the same size, and they could store across it in several tracks 1 bit. The earlier tapes didn't store that much information, but that technology improved too. So you could store millions of characters of information on 1 reel of tape. Well, that would be called a master file. You would build it with a program that would cause a tape device to output it, and there would be your master file. And that master file might be used to produce various kinds of reports throughout the day, mailings, whatever, promotions. But as things were sold, every one of those sales generated a transaction. Who bought it? How much did they buy? How much did we charge for it? What did it cost to ship it? Where do we send it? All that stuff. So these transactions build up, and at the end of the day, you combine the master file with those transactions, and you create a new updated master file. And you at the same time create some reports, because some of the transactions might have been entered incorrectly. There's some bad data, so they bounce out. They have to be fixed. Come in the next time. This whole cycle of updating became entrenched in business, and it really fit accounting very well. With accounting, you do this. You run it on a daily cycle, and then you balance it at the end of the month, and at the end of the year, you have to produce a bunch of reports, like a payroll system. This worked great, and it's called batch, B-A-T-C-H, because you have batches of data. And there were lots of different jobs that had to be done. You know, there's accounting, there's sales, there's this and that. There might be hundreds of programs. So this machine was programmed to run many jobs at the same time. And that was called an operating system. And you're familiar with that term, like Windows is an operating system, and Unix and Linux, and Apple has versions of these systems, these operating systems. It's software that governs the computer. So the nature of this was batch. It was intended to manage a lot of these jobs coming through at one time. And as one job hit a point where it needed to read more information in, there was processing power available to work on some other jobs. So they all went through in little increments, switching between these jobs. Well, operating system got very refined for doing that, and that's the way things worked until the late 60s when people realized, look, there's stuff we could do with a computer that doesn't fit that model. And one of them is selling tickets on airlines, because air travel picked up after the 50s. So how are you going to do it? I mean, I remember buying a train ticket in 1970, and I went to the train station. This was in Los Angeles, and I wanted to take a train from there to Chicago and back. And the guy had these books and things, and he could look up. He says, well, we can write you a ticket on that date from here to Chicago, but I can't tell you about the return trip. I've got to send a telegraph. I've got to send a wire to Chicago where they maintain the records on the trips coming from Chicago to LA, and 3 days from now I can tell you if we have a seat for you on the train coming back when you want to come back. One of the last times I took the train, I said, this is ridiculous. Already go buy an airline ticket and know you had a ticket for both ways when you wanted to fly. Well, what made that possible was using computers a different way. Because somebody here had to be able to go in and get the information and pull it back, give it to you, go back in and put your name on the ticket, and then print you out something saying that was there. You expect this these days. That's called online processing or interactive processing. And these machines weren't invented to do that. That wasn't the way that they were used. But what happened was programs were written to make them able to do that, and the program, and there are still careers in this, the program to do that actually looks like it's just another one of these batch programs, but it's managing all these terminals and all this communication going in and out. Very complicated stuff, and mainframes to do online processing, it was rather complicated, and it still is, but it's still used in very large organizations because no matter how powerful networks of PCs have become, these kinds of machines tuned up to do this can do thousands of transactions a second. And I'll give you a comparison. When DePaul still had a mainframe, this was before 2002, it was programmed with this older technology, but when registration came up, there was absolutely no scheduling of registrations. You registered, registration was open, go at it, everybody registered at the same time. because the thing could do thousands of transactions an hour. There wasn't any bottleneck. Everybody could hit it once. It was very efficient for the purpose. Now, it had clunky green screens. It didn't have windows. It didn't have all this other colorful stuff. But when you wanted to get registered, there you were. You had it. And then when we replaced that with the more modern technology was when we had to start staggering things. Okay, seniors can register here. You have a registration slot right here. That's when you can start. To sort of spread it out so it didn't all hit the system at one time. Because now, if we can get 20 transactions a second through, it's a big deal. Because the technology is different. It does more. It's friendlier. But it's not, for this purpose, as powerful as the old systems were. And the system that we had was essentially an old mainframe, some other software associated with it, and a lot of dumb terminals out there. Now, that's just you pays your money and you take your choice. But for online processing, huge businesses still use this. Large banks, large organizations, insurance companies. The movement is away from this, and I'll show you what's replacing it. But that idea of getting computers to be interactive was not the way computers were invented and programmed in the first place. So what happened later? Well, in this era, here's what came about. Organizations had centralized their computing resources. So you had this mainframe, and what I showed here was all these technical people programming it. They were all located in what's called the information systems area or information technology. So there were a lot of jobs in that area. Now the number of jobs there has diminished as this occurred. As computers became cheaper, the circuitry that was developed made them somewhat cheaper. This era from 1970 to 1990 was mini computers. And mini just meant it was a small, centralized computer. So a department might have their own computer. They sort of looked like this. I mean, it was one computer for a lot of people, but it wasn't in the central information technology area. So this made for management problems. What happened is these machines sometimes came in because there were certain things that people like engineers wanted to do that just didn't fit with the mainframe. So they went out and bought a mini computer. Maybe they sneaked it in the budget and they got it to do some kind of computations. Then they started doing other things with it. And then somebody over here in another area did the same thing, but they bought a different kind of computer from some other mini computer manufacturer. There must have been a dozen of them around. And that happened again and again. So these people might have been sort of happier with what they had because they weren't dealing with this bureaucratic central organization to get to use a computer. And these tended to be much more interactive right off the bat. They were developed to kind of talk to terminals and not to run these kinds of big batch jobs. So you see, what happened here was kind of like a personality conflict between the way technology was used. However, companies found a real problem with this, and here's what happened. First of all, if you're going to manage this, and there's one kind, and there's one language that's used for it, and a set of procedures on how to develop a system, how you figure out what the computer system's supposed to do, what's going to happen if this goes wrong, that goes wrong. That's called systems analysis. And that's not very glamorous stuff. That's a lot of talking to people and figuring things out. It's not programming. It's like making diagrams and writing documentation and stuff. Well, that's part of what was done here. Part of what was done here in this organization. But when people started getting their own computers, they were so full of joy to use them, they didn't want to do the drudgery. So many of the systems built out here were kind of informal. And then when personnel changed, somebody who cooked up something here that worked well, the organization comes to depend on it, that person moves on, it doesn't work. Now it breaks. And there's no documentation. So how are we going to make this thing work? Ultimately, the problem came back to the computer people. Well, they didn't like this because they didn't have any hand in doing this. They didn't even know what it was. They didn't have anybody trained on that machine. And all of a sudden it drops in their lap, like now it's your responsibility. So this organization was mostly against this phenomenon. So you have people out here who think that the centralized organization isn't responsive enough. It's bureaucratic. It takes a long time to get something done. And they want to do it their own way. But then the organization, the upper management, sees a problem because they say, well, this isn't supportable. You're not trained out here to do all this drudgery that's necessary to keep the thing running. So eventually what happened, technology moved on, and it sort of re-centralized in this way. Notice the difference here. Here, these are dumb computer terminals. They just communicate. They don't have any logic. They can't do any computation. They don't have a disk. They don't have memory. It's just a machine that talks. You hit the character here, and it sends a character to the computer. But here, once little computers, personal computers, became commonplace, those dumb terminals were by and large replaced with computers because a computer could run a program that made it look like a terminal. So you could do that with a computer, but you could do a lot more. And ways were developed to put these into local area networks. And since they could be connected, they could do email. So now you could communicate a different way across the organization. And bigger versions of these, called servers, they're just PCs, but they're much more rugged. They're meant to be run all the time. So they have heavier duty components, heavier duty disk drives, and they run all the time. So they're kind of like, police cars are heavier duty cars. You or I might buy a car, we might speed down the street, hit potholes, whatever, and eventually the axle breaks. Well, a police car presumably is built heavier duty, so it can keep doing that and chase offenders and everything else. It's a heavier duty kind of a vehicle. Well, that's what servers are. They're a heavier duty kind of a personal computer with a lot more memory. So those things came in and were centralized, and applications, that is software that the business used, began to be put onto here, sort of moved back from this environment to here. So this re-centralization occurred. And many times it happened with servers and the old mainframe sharing the same machine room. The air-conditioned special place where it's kind of secure, and that's where the machinery is, care and feeding of the machine occurs there. So this led actually to, with the internet coming up, connections to the internet, so these things became more capable and could acquire information from outside the organization. Well, think about this. What does this do in terms of careers? Now you've got a lot more concerns about security. So one of the things this course looks at is careers in computing too. One of the big careers right now is security, computer security, and telecommunications. That is, maintaining the technology and administering all the stuff necessary to keep the communications network working and to keep it secure. So people with a mathematical bent or who like to solve puzzles, some of them go into network security where it's very high-paying jobs and it's very hush-hush. Once a company has a problem with security, they tend not to publicize it, but they want to have expertise that prevents that kind of a problem in the future. So this gets into all sorts of interesting things. Anyway, this was kind of a transition. What happened was organizations found that the more they could do this way, presumably the less expensive it was, sometimes not, but it was more capable. It worked in the modern environment better than this old approach. So organizations that could actually did this. They wheeled out the mainframe, like DePaul did in 2002, and now all we have is a bunch of servers. And they run a whole different kind of software, and their whole approach is different. They're intended to be interactive. But it's a more complicated environment than it was before. So although I've shown fewer people here, these people each have to have a whole different set of skills now. It isn't just one language and one environment. There's all sorts of different stuff. And that makes for even more careers. And data now is handled differently. It's not just in files. We'll talk a little bit about what files are later, but they're in databases. So they're more flexible arrangements of data. So this is kind of where we're at right now. Many organizations are working like this. And of course, some of these aren't even connected with wires because we have wireless, which is another technology that's improving all the time. So I'm sure you're used to this. You probably have Wi-Fi in your home. You have Wi-Fi around here with a little security arrangement to hook into it. And the other day, I used to have Wi-Fi with AT&T, but I thought I was paying too much for it. So then I went to another company that had a little modem, like a little USB drive. You plug it into your computer and it talks to the network out there, wide area network. But there was not Wi-Fi. It was just the one computer, but I wanted Wi-Fi. So I went back to the same company, and they got me a little device about this big that's a portable Wi-Fi hotspot. So that's what I have at home now, plugged in, and that gives me Wi-Fi in the apartment. But I can unplug it. It runs on a battery for 4 hours, so I stick it in my briefcase, and I carry my little Wi-Fi hotspot around with me. So any device that I want, like this little iTouch that I bought that's got Wi-Fi, I'm sitting on the L, and I'm doing my business here because the hotspot's moving with me. And it's just talking to the internet out there. So that sort of thing it opens up possibilities. People expect this. They expect to be having portable connections like this to the internet, and all that makes for even more in the way of careers and jobs to manage all that stuff, to make it seem easy. Well, where's it go from here? Here's what's happening these days. Some people are proposing this. Okay, what's different here between this and this? What's different is this bunch of servers is gone. Here, all we have is people in a little box that connects us up with a very high-speed connection to what's represented as the cloud, but it's really the internet that's out there. Later on, we'll take a look at what the internet looks like physically, just this huge network of computers out there all connected together by way of these information protocols that are very standard now. So all of that computing power that's out here, part of that is these big vendors that maintain very huge server farms, they're called, like thousands and thousands of servers to support their own business, like Amazon and Google. Very large organizations. They have tons of servers. And what they decided was, well, why don't we rent some of our processing time to other people? Because they've figured out how to manage networks of thousands of computers. In fact, I understand that Google, what they do is they just buy motherboards by the thousands, and they have rooms that just have cork walls. They just stick them up with a pin on the wall, and that's the computer. That's a server right there. I mean, not even in a box. It's just hanging there on the wall with a fan blowing on it, and when it blows out, throw that one out and put another one up there. And they can switch these around very fast. So, I mean, they've worked out ways of supporting these things. That's their business. So, people who are claiming this way of doing business, here's the advantages of it. This is scalable. That means if you need some computing power now, okay, but your business it runs in cycles. At some time, you're going to need 10 times as much processing power. Maybe to process an election or something, or some news event, whatever. Or you're a news organization, and you normally have this level of work, but when the Olympics comes along, it's 100 times bigger, because there's more people who want information. So how do you do that? If you want to maintain all your own equipment, are you going to buy enough and maintain it to cover the peak and then have it not used most of the time? Well, something like this, you just sort of buy what you need from vendors who have a lot of it. So computing this way is kind of like what's called a utility. It's just like the electric utility. If you want more power, buy more power. The meter spins faster and you pay more that month. And when you don't use it, you don't use it. It's the electric company worrying about capacity and how to meet everybody's need. So this sort of a thing has implications, definitely. Look at this. If you have this organization, first of all, somebody had to arrange to buy this thing or lease it. Those are administrative people that you may not need if you go to this. And when you have this, somebody has to run this. And it has to have a place to be, like a machine room. And all that takes people to operate and expense to provide. And then this requires software, the operating system, and that keeps changing. We have here at DePaul, we have maybe about 100 people in the data processing area, and a number of them are dedicated to every week changing the software based on what the manufacturers of the software say needs to be fixed. Called patching, like patching a tire. But it happens all the time. Changes come out several a day sometimes, and they get bunched up, and on the weekends they have to go in there and fix this stuff and change it. So all of that takes highly skilled people if you're going to be running this yourself. Well, that's another expense that presumably you escape if you do this, because somebody out there who's providing the power to you is the one who's doing that. So this has advantages, but it has downsides too. People worry about security. Here, the notion is, well, all your data is right here. All my sensitive data, my trade secret data, the stuff that the government says I shouldn't reveal to anybody else, it's all right here. I can protect it, maybe. But hacking occurs quite a bit, and since this is all connected to the internet, that's another specialty that people have to watch out for. How do you protect this and keep intruders from coming in and stealing stuff? Well, here the same concern. If you're sending your data out here now, where is it? Who's got it? Who has access to it? How do you secure it? Well, there's means of encoding it and encrypting it and all that sort of thing. But you know, this question about how do you trust it? And who's liable if somebody runs off with information that they shouldn't have? So those concerns have to be addressed too. And this is by no means all over the place. This is just, I'm just telling you this because you'll see it in the literature. This cloud computing. And what happens basically in a field like this is that somebody cooks it up, then they start having conferences on it. Conferences serve the purpose of giving executives nice places to go at company expense. You know, conferences occur in Orlando and Hawaii and Hong Kong and all sorts of kind of places because executives like to go to these places, and then they talk about these new developments, and some of them come along, some of them don't. But cloud computing has sort of evolved to the point where some people actually are doing it. And in fact, there's a little bit of that going on even in this course, because where you're doing the exercises is not a system maintained by DePaul. I'm just renting that from a company, I think they're in Arkansas someplace, and they run a learning management system named Moodle, which is open source, and we'll talk about that, the implications of that. It just means it's widely available. And I pay them a little bit of money, and they run the stuff for me. And I don't have to maintain Moodle. I don't have any computers out there I'm paying for. In fact, it's ridiculously cheap. I pay them $1 per student. And that's how I get access to the system for your behalf. But it's a very responsive system, and I never have to worry about it. And I think some schools are probably going to go to that model as opposed to having their own software and running it themselves, because it's very expensive to do that. And it's sort of like this, except, well, it's like this to the extent that I don't even know where it is and I don't care. I'm sort of trusting them to do this. And they do a very good job of it. So anyway, that's kind of the big picture that I wanted to give you. Now, the first of the projects is out there now. If you have time and if you want to do this particular one, it's available for you. They'll be more available in a day or two, because basically I'm coming up with these to revise this course as the lectures go on, and the next lecture is Thursday. But this one is just kind of an interesting thing. What I want you to do here is to, if you have PowerPoint, I want you to come up with one slide that has a horizontal line across, and then duplicate it 10 times. And put one slide up front that just has your name on it, so I know who submitted this. Basically, you have 10 slides here, each with a horizontal line. And that line is going to represent 10 years. So label the first of these 1900 to 1910. And the next slide, 1910 to 1920, and you get the drift all the way through the 1900s. Then I want you to do some research with any of these places, starting perhaps here, and figure out enough of the history, not ancient history here, you can read through that if you like, but down here, this is going to illustrate for you all sorts of things like I talked about. For example, here's that mechanical device from the 1830s to attempt to do computation. And you can see these dials that read out numbers and all these cranks and things. Very complicated. I'm not really sure it worked too well, but at least some models were made of it. Another one. And then this was that mechanism. See the threads in here? These cards with the holes in them are actually determining what the pattern of the weaving is going to be. But what we're looking for here, starting at this point, this was a machine that stored information on paper cards and actually automated the census in 1890. The fellow who invented this thing sold it out to IBM, and IBM did a big business in this in the 1900s onward. IBM here. And some of the developments in computers and storing things on paper tape and whatever. But go through this and some other research you can do on Google and build a timeline using these slides so you can put a dozen events in there, the most significant events leading up to the present in the development of computers. Some of the things I've talked about, and you decide what's the most significant events. But put them on this timeline. The reason I'm doing this, I'm suggesting you do this on PowerPoint, is that this you can submit electronically. I don't want this on paper. In fact, I used to do assignments like this, and I would give people adding machine tape, very long. I said, draw a line down this way and mark it off, and then you turn it into me, and then I would grade it by treating it like a scroll, and reading through it. It's not going to work for an online course. I don't want the paper. We need something electronic. So if you can do it in fewer than 10 slides, well, that's fine too. I'm just suggesting 10 to keep things kind of simple. And you sort of place the event on that page where it fits. If you're in the 1920s and this thing happened in 1925, well, take the page that you've labeled 1920 to 1930 and stick it in the middle, because that's about 1925. earlier or later. So anyway, it's just a timeline done electronically, but that, if you're interested in it, this will be one of the 5 projects that is available to you, and you can get started on that now. And I will have up very shortly the other projects, which will look probably pretty much like this, although I may get some other ideas in here, so some of the other ones may be a little different than that. Don't start on the ones in red until they turn black and they're documented. Otherwise, you might wind up going off in a direction that proves unproductive. So anyway, that's where we're at today. Can I answer any questions for you?
What about like Campus Connect?
Uh-huh.
What about like Campus Connect? Is that run by like one server or?
Well, actually, DePaul has probably 50 to 100 servers, and they don't look like the computers you see here. They're kind of long, flat pieces of equipment that fit in a vertical rack. So the machine room kind of looks like it's just panels of stuff, and each one of these horizontal things is a server in itself. And Campus Connect is just one chunk of software that runs on some of those. So these days what happens is many servers may be running the same thing, and it attempts to share the load between them so that it isn't just one machine that's bogging down. And even one machine might have multiple computer chips in there, multiple thinking parts. So it's rather complicated how they do it to try and spread the load out across them. But yeah, Campus Connect is just a piece of software that sits there and it listens for your input on the web. So when you say campusconnect.depaul.edu, you're sending a message to the internet, and that server picks it up. It gets its address, and then it responds to you with the screen, and then you put information in. And the whole system, in fact, everything that's behind Campus Connect is software that DePaul has licensed to run, and there's people down there running it and maintaining it. In fact, DePaul is very much in this model right here. Very much that model. And there's a lot of people connected with these things on the 5th floor of the Computer Science Building and in the CNA Building that actually do this kind of stuff. And you don't usually see them because they're kind of off in offices. They don't have any public visibility. Okay. No other questions? Well, we've only been here about an hour, even less. And I don't want you to think you're not getting your money's worth. So I will sit here as long as anybody would like to chat about things or ask questions or pursue whatever. But the class is actually, it lasts until 11:10, so I don't want to shortchange anybody if you want to stick around. Somewhere along the line, I'd like to get some input from people about this notion. I suspect people like the idea of not having to buy a book. I would like to find out if you think you're being shortchanged in that.
I only have to get like 6 textbooks for one class and use like 2 classes.
Yeah, that's what I was...
There's so many classes that I don't even end up buying the book. I'll just find them in class and photocopy.
Oh, really?
The book, yeah.
Wow. I would probably do the same thing. I mean, it's ridiculously expensive too. But what cracks me up about this stuff, and I've done this in other classes too, there's so much stuff on the web that's available that, in fact, let me just, before you leave, let me show you something else that is a resource here that I will work into this class in the ways that might be appropriate. But a couple of years ago, when I was assigned to teach a course a little more advanced than this in information technology, but an exposure to it, I was so turned off by the textbook that had been assigned, which cost $125, and it was 3 years old, which was old by computer standards, and all the fellow had done was take stuff that's readily available on the web and put it into print form. And I thought, this was nuts. So I said, you know what, we'll make that book optional, and I'll come up with an online way of supplying the information. So that's where this workbook came from. But what happened here was, I just decided, okay, I'll make it like a book, and these are all things from the web. So when we're going to talk about this, go on out here and look at this, and there's a definition. There's no reason for me to take that and print it in a book. I mean, read it here if you want to. And the same business goes here. There's things, there's explanations. It just takes time to find them. But what I found was there are better things out here than you could find in a book. Because take a look at this. this course started talking about computer hardware. So in order to see how this works, see, this is animated, but here's the interesting part. That's how a dot matrix printer works. That's what it's doing. So instead of me trying to describe that in words or looking at a static picture, here's a free place on the web. Well, this makes it much easier for everybody to understand it. And the same thing goes, this actually did a nice job here on inkjet printers too, because it shows you how this thing is doing the same thing the dot matrix did, but it's squirting little dots of ink out as it moves across the page. So I figured, wow, you could do much better by doing an electronic textbook. The thing is, it chops out the publisher. So it's not a very popular thing from the point of view of who's publishing this, and it's not popular from the point of view of who's writing it because they don't make any royalties on this. So what? I don't care if they get mad about it. I still do this. And actually, nobody around here gets mad about it. It's just that the publishers probably aren't very pleased because in this course, too, you don't need to buy an expensive book. But one way that this is marketable is there is a printed workbook that goes along with this. And in fact, it's much less expensive. Typically, these cost about $25. And there's a publisher that I go through that doesn't. See, here's another, whoops. Well, here's a workbook for a different class, but let's take a look at this one. This one doesn't have music associated with it. Okay, where is it? Oh, gosh. Somewhere along in here, there's a picture of a workbook that we published with this. A friend of mine and I did this one. And it reduced the cost of the book to about $30. It's 300 pages, and it has all this text in it and everything else. And we just wrote up to have a public service. It was a whole lot nicer than trying to stuff a very expensive book down people's throats. But in this case, I think I'm just going to leave electronic. The thing I'd like to find out is, well, really two questions. First of all, does anybody, when I make something available electronically, like the book for this course, does anybody ever print it?
I did, but just because I highlighted it. So.
Okay. And if there were a published version of the book available for less cost than it cost you to print it, would that be appealing or not?
Well, yeah, it costs less than printing.
Yeah, because it costs.
How much did you pay to print it?
I mean, I did it at work, so I just like budget at school, it'd be 8 cents a page. And
Yeah. Yeah. Well, I'm aiming at this thing as being very inexpensive because, you see, when the printer does it, they print it two-sided, and then they bind it up. So it's a little
But isn't the
handier.
binding that costs all the money?
No, the binding, I have the guy use it just a tape binding. It's very flimsy. You can pull it apart if you want to. Sometimes I have pull-out sheets if I was doing a class in class, and I have them pull it out, and that's a quiz.
I had a class where they did that. Like, you just print out everything and then put like a little plastic binding on it. You could buy it for $10 if you wanted.
Right, right. That's what I'm aiming at with this sort of thing. But really, there's an advantage to electronic because I can put the hyperlinks in there and they're active. So, you know, when you look at it on the computer, click on it, and then you go someplace else, and then you come back. So to me, it's like, wow, that's really the way you want this stuff to be. So I'm sort of on a kick to chop out the publisher and all that business. It's just something that we do around here. This is the way you learn the stuff, especially with 10-week quarters, because textbooks are written for semesters. You're always going to have in our environment that very thing. Well, here's the book, but we're only going to read these chapters of it. So you probably feel kind of rook because you spend a lot of money on the book and you're only using part of it. That's silly. Anyway, 1 hour. I will be here another 30 minutes if you want to hear some jokes or any answers to any questions. And we'll see you on Thursday otherwise.